Okay, we're going to derive a thing called the impulse momentum theorem here. It begins from Newton's second law, not too surprisingly, so sum of the external forces equal to ma. In the past, we've done things like this, but you may remember in the past, we did some funny chain rule tricks with the acceleration, and we did that to get the work kinetic energy theorem. In this case, we're just going to deal with it straight. So, acceleration can be written as dv dt. Then we will separate the infinitesimals, and we'll integrate the two sides. So we have the integral of the net external force with respect to time equal to the integral of m dv. We'll integrate that from an initial to a final velocity. Actually, I'll keep that just as a v. So we'll have integral of our force with respect to time equal to mv final minus mv initial. Then, of course, momentum is defined as mv. So we can just write this as the integral of the external force. Ooh, I should keep the vector symbol on the top. With respect to time, equal to the momentum final minus the momentum initial, or integral force with respect to time is the change in the momentum. And that is essentially the impulse momentum theorem, with the impulse. Unfortunately, the symbol for impulse varies from textbook to textbook. Some use a capital I, some use a capital J, is equal to the integral of the external forces with respect to time. All right, we can also write that as the average force times the elapsed time, and we do that frequently. And we'll talk about that before we call this section done. Why can we do that? Well, imagine you have a force acting over a time. It comes up for a while and it comes back down. There's some whole time interval over which it acted. If we think about the average value of it, imagine cutting this up and moving the slices over so we get the average value. We can actually take that average value times the change in time, and it will give us the same value as the area under the curve. So that is the trickery going on there, and why we can use f average times delta t as a substitute in many cases. It won't tell us exactly what's going on with the force. The peak force will be higher. It'll have other times where it's lower. But it'll at least give us an idea of what the force rises to as sort of an approximate value, which sometimes is all we really need. All right, that's actually it for proof of the impulse momentum theorem. We'll be making a fair amount of use of that coming up next, so stay tuned.